Okay, today we're going to go over Chapter 20, which is about hypothesis testing for sample proportions. A hypothesis is an unproven theory. It's an idea that we tentatively hold on to while we are testing out our theory. If we choose to keep it after our test is complete, we are retaining the hypothesis. If we throw it out after our test is complete, we are rejecting it. In life, you would see this when you do a science fair project. In a science fair project, you always start with an initial hypothesis, you do your test, and then you either hold on to your hypothesis in the end, or you say, no, I was really wrong, this is what really happened. You would also see this when you serve on a jury, which is something near and dear to my heart today. I am currently right there. You hold on to the idea of innocence as your starting hypothesis until you either reject or retain that idea in the end. If you reject that idea in the end, you're deciding that the defendant is guilty. Hypothesis testing and statistics. Our starting hypothesis is called the null hypothesis, HO. That's not HO, it's HO, the null hypothesis. You will test the null hypothesis when you do your statistical test, and then you're going to use your results to either decide to retain or reject the null hypothesis. In every statistics problem, there's something called an alternate hypothesis, HA, not HA, HA. This is the alternate hypothesis. If you reject the null hypothesis, then you are accepting the alternate as the truth. Retaining the null hypothesis does not mean that the null hypothesis is true. It means that we failed to reject it because we don't have enough evidence from our sample to reject it. Just like when you're serving on that trial, on the jury, if you don't have enough evidence to say that person is guilty, you're not saying they're innocent, you're saying that you don't have enough evidence to prove them guilty. Okay. Here's our example. Is there a home field advantage in baseball? In the 2002 Major League Baseball season, 2,425 regular season games were played, and the home team won 1,314 times, or 54.2%. If there is no home field advantage, the home team should win about 50% of the games played. Is this deviation from 50% explained from just natural sampling variability, meaning that every time you draw a sample there's going to be a little fluctuation in the results? Or is this evidence in this sample to suggest the presence of a home field advantage? Okay, here's our first step. We're going to state the hypotheses HO, the null, and HA, the alternate. If there's no home field advantage, then P would be about 50%, so our null hypothesis HO is that P equals 50%. Our alternate is that we think it's a little bit higher than that, meaning that there is a home field advantage, so our alternate would be that P is greater than 50%. Check the conditions. We need a simple random sample. We've got that. We're going to assume that this season, the 2002 season, was randomly selected from all the seasons in baseball, and there's no special reason it was chosen. Independence means the outcome of one game is not influencing the outcome of another game. There's no revenge factor considered here. We're assuming that it's completely independent. Population size. 10 times 2,425 games would be 24,250 games. You have to have at least that many games played in professional baseball ever, and I'm pretty sure we've met this condition. 10 successes and 10 failures. We had 1,314 games where the home team won, and 1,111 games where the home team lost, so we've met this condition as well. Okay, now we do the actual calculations. This is all done in the calculator. The mean is the null hypothesis, which here is 50%. For the standard deviation, you're doing the square root of PQ over N, which P and Q are the null hypothesis and the opposite, okay? So P is 50%, Q would be 50%, not the specific sample percentage that we got. That comes later when we do our test in our calculator. So 50% times 50% over 2,425 games, square root that, standard deviation is 1.02%. Here's how we do the work in our calculator. Go to Stat, Tests, and you want to pick number 5. Now the first thing you're going to see is something called PO, that's called the null hypothesis in your calculator, and you're going to put in 0.50 to represent 50%. Next is X, that's the number of successes, which here we had 1,314 games that were successful, meaning the home team won. And then N is the sample size, which here is 2,425 games total that we played. you want to pick greater than PO, that's the third one on the far right on the next line, because the alternate hypothesis we're looking for is the possibility that P is higher than the null percentage of 50%. Now when you actually go ahead and push calculate, we get a z-score of 4.1223. That kind of is information that's good to know, but it's not really all that important. The idea of the z-score is that if you're more than 3 standard deviations from the mean, then you're very far away from the mean, and that's a bad thing for your null hypothesis. It means it's not true. Here we had a probability, or a p-value, shows up in your calculator, p equals 1.877 e negative 5, which means that we have almost 0% chance for our p-value. The p-value is the probability of your sample's results occurring naturally. Since this probability, or p-value, is almost 0%, there's almost no chance of our sample's results occurring naturally. What that means is that the null hypothesis is not true and it should be rejected. Here's how we state our conclusion. If we reject the null hypothesis like we did here, then we're saying that we reject the null hypothesis of 50% because there is sufficient evidence from our sample to conclude that there is a presence of a home field advantage. There is sufficient evidence to say that there is a home field advantage. Okay? You reject every time your p-value is smaller than 5%. If the p-value had come out to be more than 5%, we would have retained the null hypothesis, meaning held on to it. There would be more than 5% chance that our sample's results occur naturally, and what you're saying is that you have insufficient evidence from your sample to conclude that there is a home field advantage. You don't have enough evidence, so you have to hold on to the idea that the null hypothesis could possibly be true. HO versus HA. HO is the null. It's always P equals and then whatever percentage is your baseline percentage. HA could either be greater than, if you think that the true p-value is higher than what the null is saying. It could be less than, if you think that the true percentage is lower than what the null is saying. Or it could be not equal to, meaning that you don't know whether it's higher or lower, but you just think that it could possibly be higher or lower. It's just different than what the null is saying. Here's another example. It's a medical fact that male babies are slightly more common than female babies. We want to know whether the proportion of male births has changed from the established baseline of 51.7%. To test this hypothesis, a study in India reported in 1993 that 56.9% of one hospital's 550 births that year were boys. Could this variation be explained by natural sampling variability, meaning that there's going to be variation every time you do a sample? It's going to be off a little bit. Or is there evidence in this sample to suggest that there really is a change in the percentage of male births? Let's go through our 4 steps. First, stating the hypotheses. The baseline percentage is 51.7%, and this is going to serve as our HO, our null hypothesis. The alternate is that we think it might have changed. We don't know high or low, but we think it's changed. So P is not equal to 51.7% for the alternate. Let's check the conditions. Okay. We assume that this year, when we did the test, was chosen randomly among all the different years where births occurred at this hospital, and that each birth is independent from the other births. We assume that there have been at least 5,500 births at this hospital, meaning 10 times our sample size. And we have at least 10 males and 10 female births in this sample, so we're okay, we've met that last condition as well. Now we're ready to do the calculations. Go to stat test number 5. PO is your null hypothesis, that's 51.7%. Put it in as decimal form though, 0.517. X is the number of successes we had. Now they didn't tell us how many successes we had in this problem, but they told us we had 56.9% times 550 births. So if you do 0.569 times 550 births, you get like 312.95, but you have to round that to a whole person. So you want to put in 313 whole people. Successes here would mean male births. N is the whole sample size, which is 550. For the alternate hypothesis, choose not equal to PO, because the alternate hypothesis we're looking for is that we think the p-value has changed, not necessarily high or low, but we think it's changed from what the null hypothesis used to be. when we do our test, we get a p-value of 1.45%. This is lower than 5%, and so since our p-value is less than 5%, there is a very little chance that our sample's results occurred naturally. Therefore, the null hypothesis is not true and it should be rejected. Our sample is indicating to us that the percentage of male births has in fact changed. Remember, if that p-value is higher than 5%, you want to retain the null hypothesis. Here, we're rejecting because that p-value is less than 5%. Using a confidence interval to test a hypothesis or to just kind of back up your results. Let's find a 95% confidence interval for p based on our sample proportion. To do this, we go to stat test A, just like we did in the last chapter. X here is probably already in our calculator. Again, it was 313 successes. N is the sample size, which is 550, and our confidence level is 95%, so 0.95. Now when you hit calculate, we get our confidence interval running from 52.771% to 61.048%. Is the null hypothesis, 51.7%, contained in this interval? No, the null hypothesis is outside this interval. It's actually smaller than this interval. So does that mean we should reject or retain the null hypothesis? That means we should reject the null hypothesis because it's not contained in this interval.